Okay, guys, sorry, got interrupted. So successive ionization energies. So successive, it just means that we're going to take one electron off after another. So we're going to look at the amount of energy that it takes to take an electron off, and then take another one off, and then take another one off. Okay, so let's look at this. So let's just define some of these things. What is the second ionization energy? It is the energy required to remove an electron from a 1+ ion. What that really means is the energy that it's required to remove an electron from an ion that already has one electron removed. It already has a 1+. So if the second ionization energy is how much energy it takes to remove that second electron that we're taking off. So the third ionization energy, what do you think it would be? It's pretty much the same thing. It's the energy required to remove an electron from a 2+ ion. Okay, so basically we keep on taking ions off or electrons off and making a 1+ ion for the first one, a 2+ ion for the second ionization energy, and a 3+ ion for the third ionization energy. So do you think the second ionization energy of beryllium is going to be higher than the first ionization energy? Why do you think so? Okay, just think about this. When I take that first electron off, that first electron, I now have one more proton than electron. Doesn't it mean that the protons in the nucleus are going to be able to pull those electrons in even tighter? So those electrons are going to be even closer to the nucleus. Okay? So the electrons become closer to the nucleus. So it makes it more difficult every electron we pull off because those remaining electrons get pulled in even closer to the nucleus. Now let's look at beryllium. So the first ionization costs us about 900 joules to do it. The second, almost double, 1760. But then on the third, look at this. This goes up almost 9 times. 9 times, not doubling, but 9 times. Why do you think that third ionization energy is so steep, so much energy? Let's look at the electron configuration for beryllium. So if we look at beryllium, we have 4 electrons. Okay, so we're going to have 1s2, 2s2. So we have 1s up and down, 2s up and down. We're just going to write it out completely. Okay, so that third ionization energy, we've already taken these 2 electrons off. We are now working on taking this electron off. Notice what's different about that third electron. That third electron is coming from an inner shell. That inner shell is even closer to the nucleus. That's why there's such a big difference between the second and the third. We have now gone to an inner shell. Okay? Okay, to take the third electron, we have to take an electron from an inner shell. Essentially, if I have one s2, don't I have the noble gas configuration of helium? I even have 2 more protons, so the electrons are going to be even tighter than helium. So not only am I taking from an inner shell, I'm also breaking a noble gas configuration. Breaking a noble gas configuration. Okay, so let's write the configuration. Let's write the noble gas. Let's write the configuration for boron. So if I look at boron, I have 1 more electron. So I will have 1s up and down. I will have 2s up and down. And I have 2p up. Okay, so where do you think that big jump is going to be for boron? I'm going to give you a minute to think about that. What did you say? Did you say right here? We can pull off 3 electrons, but once we pull off that 4th, that's where that big jump is going to be, because we are going down to a lower shell. Okay, so the fourth ionization energy is where that big jump is going to be. Okay? All right, I want you to look at these next ones. So let's look at sodium and calcium and aluminum. So sodium, we have 3s1 configuration. Calcium, after the noble gas, we will have a 4s2 configuration. And aluminum, after the noble gas, we have a 3s1, or sorry, a 3s2, 3p1 configuration. So I want you to think about this. After which electron, first, second, third, fourth, the big jump will be the first, second, third, fourth ionization energy. So to get to a noble gas configuration for sodium, I just have to pull off 1 electron. So after that first electron, I now have a noble gas configuration of neon. So the big jump for sodium will be that second ionization energy. Okay, I want you to do the same thing for calcium and aluminum, and we'll check in just a second. Okay, you ready to check? So calcium, since I have 2 valence electrons, after that second electron, the big jump will be on that third ionization energy. And aluminum, I have 3 valence electrons. So after that third electron is pulled off, that 4th electron will be the big ionization energy. Okay? So if you want to check it out on the periodic table, let's look at this. So we were looking at, let's highlight these a different color. We were looking at sodium. Notice it's got 1 valence electron. So I can pull the first one off pretty easily, but pulling the second one off is going to be really hard, because pulling that first one off, I go back and have neon's configuration. So making it like fluorine in terms of electrons is going to be really difficult. The next one, calcium, I've got 2 valence electrons. So I can pull these 2 off pretty easily. But once I get to argon and try and pull that third one off, it's going to be pretty difficult to do. And then last but not least, we're going to look at aluminum. So I have 3. Sodium gives me 1, magnesium gives me 2, aluminum gives me 3 valence electrons. I can pull those first 3 off pretty easily. But getting back to neon, once I pull that 4th one off to make fluorine, that's going to be really, really difficult to do. Okay? So let's look at electronegativity. Electronegativity is a little bit different. It is the measurement, it's an indication of the relative ability of atoms to attract electrons in a chemical bond. So we need to first be bonded with another atom. Oh, atom's not spelled with 2 T's, it's spelled with 1 T. And then we're going to compare the attraction of the atoms in that bond to the electrons that make that bond. Okay? So we have to have bonded atoms, and then we compare the 2 atoms that make that bond, and we compare the electrons and how attracted they are to either atom in that bond. Okay, so it is a relative scale. We assign electronegativities based on a relative scale. So the highest electronegativity is fluorine at 3.98, and the lowest electronegativity value is francium at 0.7. You will notice that the heaviest or the highest electronegative values are right here. We have nitrogen, oxygen, fluorine, and chlorine. Those are by far the heaviest electronegativities on the periodic table. You'll notice also that the general trend of electronegativity, if we are increasing in electronegativity as we go from left to right, we are decreasing in electronegativity as we go down. So the electronegativity trend across the periodic table is just the same as ionization energy with one big difference. The one big difference is, notice, we do not have any electronegativities for the noble gases. So why don't we think we have electronegativities for the noble gases? Why is there that difference? Now remember, one of the definitions that I said is we are sharing electrons in a bond. Do the noble gases bond? No, they don't. So because the noble gases do not bond, we don't have electronegativity values because we can't see what their relative strengths are in a bond because they don't interact, they don't react. So let's look at some practice problems here. Arrange the following elements in order of increasing atomic radius. So I'm going to grab my periodic table and I am going to close this out. I'm not going to save it so that I can open it back up as its blank copy. And we're going to highlight these atoms again. So we want to compare. Let me make sure I've got my highlighter going. So we are going to compare strontium. So let's highlight strontium. We're going to compare tellurium. We're going to compare magnesium. and sulfur and silicon. Okay, and we want to know increasing atomic radius. So we want to go from the smallest to the largest. Okay, so remember, atomic radius was smallest up here near helium, and it was largest down here in francium. So the smallest, if we go to that trend, would be sulfur. So we're going to start listing sulfur first, then silicon, then magnesium. Why not tellurium? Because remember, tellurium has 2 more layers. So then tellurium and then strontium, because each period we add on a couple layers, or we add on a layer. So sulfur is going to be our smallest. So if we go from increasing, we're going to start with our smallest. We're going to go sulfur, and then silicon, and then our next one was magnesium, then tellurium, then strontium. Okay, and strontium is going to be our largest. Okay, we're going to do the same elements in terms of ionization energy. Now remember, increasing ionization energy is going to be exactly the opposite of radius. Remember, as the radius got smaller, the ionization energy got bigger. So could I take the same list and just flip it? I can. So if I do that, my lowest ionization energy is going to be my largest atom. So I would start with strontium, then tellurium, then magnesium, then silicon, and then sulfur. That's going to be my largest ionization energy. Okay, now let's look in terms of electronegativity. Now, isn't electronegativity the same trend as ionization energy? The closer those electrons are to that nucleus, the more they're going to be attracted to that nucleus in a bond. So could I take my ionization energy list and just put it down in terms of electronegativity? I pretty much can. So my lowest electronegativity is going to be strontium, tellurium, then magnesium, silicon, sulfur is going to be my largest. Now, remember, I actually have actual values here. So let's see how well our trend line goes with our values. So I'm going to look at strontium. Strontium, I have a value of 0.95. I'm going to look at tellurium, and I have a value of 2.1. Okay, so 0.95 here, tellurium 2.1, magnesium 1.31, silicon 1.90, and sulfur